So at the end of this topic, you should be able to describe the principle of coulometry and its application for determination of analytes. So look at this. This is the flow chart of electroanalytical methods or techniques available in order to determine the unknown. So you have seen this. This is the method. So divided into interfacial and bulk methods. So under interfacial, there is dynamic methods. So under the methods, the measurement of current involving current measurement is divided into two. One is control the potential, and another one is you just control the current or constant current. So this is potential static, V constant, and this is amperostatic, I constant. Okay, so under V constants, there is one uh, method which is called coulometry. Okay, so you just apply a constant potential and you measure this I, okay, the current with time, as well as at this side also involve coulometric titration, or you just apply constant current. So this is constant potential, this is constant current. Okay, so both methods using coulometric methods. So what is coulometry? So coulometry is an analytical method for measuring an unknown concentration of an analyte in solution by completely converting the analyte from one oxidation state to another. Okay, for example, you have ferrum 3, so it will reduce to ferrum 2 or vice versa. Okay, so they will completely converting analytes. For example, this is analyte, okay, the ionic species in solution. Okay, you do not know the concentration of ferrum 3, unknown concentration. Okay, so what coulometry will do is to convert this, for example, ferrum 3, ferric, to ferrous, okay, from one oxidation state 3 to 2 on the working electrode. So the process is measuring the coulomb, the charge pass. So what is coulomb? So coulomb is Q. Q equals to I current time T. Okay, this process is called electrolysis. So the chemical analysis is based on charge pass, which is coulomb. The unit is coulomb, Q. So coulometry may be done at either constant potential, we call it potential static, or V constant. So you just have a constant potential during the electrolysis process, or you also can use amperostatic, also known as galvanostatic. Static means you keep on constant. Okay, in this case, amperostatic is ampere current. Okay, or I constant. Okay, so there are two sub methods, either using potential static or amperostatic. So if the current varies during the electrolysis, so this is current is varied with time, a charge of this is 1 Faraday coulomb, okay, for 1 mole of electron. So in this equation, you also can round off this to 96,500 kilo coulomb per mole. Okay, that's a measurement of Q, okay, which is charge pass, allow us or you to calculate the number of moles of electron involved in the specific half cell reaction. Half cell reaction, for example, ferrum 3 to ferrum 2. So you must calculate how much number of mole of electron involved in the reduction or oxidation of half cell reaction, ferrum 3 to ferrum 2 or ferrum 2 ferrum 3, for example. Okay, you can measure Q. What is the amount of coulomb involved in the half cell reaction? So once you know the moles of electron involved, So you must times the number of electron and as well as Faraday constant. So this is Q. Okay, actually Q, there are two equations involving Q, charge pass. Q equals to 1 times T and also M and F. Okay, so M is the moles of reactants. So you relate these two equations, so you can calculate the moles of reactants, the reaction. Okay, IT over NF. So I is the in ampere, T in second. So this is mole. Okay, not mass, not gram, whatever. This is mole. M represent moles. So N is the number of electron involved and F is the Faraday constant. So we look at the first type or first method, which is I constant. Okay, so you just apply amperostatic or galvanostatic coulometry. In constant current, which is I constant coulometry, so the current is maintained constant, okay, till the completion of the analytical reaction, which can be detected by a visual indicator solution. Okay, you can detect the endpoint by using indicator solution. Okay, a color indicator, so you can see the different of colors, so you can identify the endpoint. Or you can use potentiometric methods or spectrophoto methods. So you can plot a graph, for example, for potentiometry. So you can plot a curve, so you know the endpoint. Okay, for example, volume, or this is current, so you can know which is the volume of endpoint. So by knowing the volume of, for example, titration or the reaction, so you can calculate the unknown concentration. So either using indicator, for example, phenolphthalein. Okay, you can see the difference when you titrate acid and base from colorless to purple or pink. So that is you can indicate the endpoint, or you can use potentiometric or spectrophotometric in order to determine the endpoint of the reaction. So the quantity of electricity required to attain the endpoint is derived from the amount of Coulomb. Okay, so you can calculate the Coulomb charge pass during the process or electrolysis process. So by uh, taking the I, the ampere with time in second. Okay, so under I constant, there are two types. One is, we call it primary constant current coulometry. So in this technique, the element to be estimated undergoes direct reaction electrode with 100% efficiency. Okay, it means that if you have analyte, okay, in this in the test solution, okay, in this case it employs 3 electrode system. Okay, so this is reference, so this is working electrode, so this is measurement of current I, or in ampere, this is counter electrode. So the unknown in this solution will, if oxidation process occur, so it will, this working will act as anode. So 100% of combustion between, for example, ferrum 3 to ferrum 2, okay, will occur at this electrode. So you are measuring ampere I with time, okay, until the change of this solution. If you use indicator solution, it's directly carried out or done on the working electrode, 100% with 100% efficiency. Okay, this process, ferrum 3 to ferrum 2, for example. So you just measure until the change of color of indicator solution. So you just stop you monitor the ampere, and you stop when you see the change of color. It means the endpoint of that reaction. So you have monitored the current, and you know how long the process of electrolysis, so you can measure Q, column. Okay, this is called primary. Primary is mean the direct reaction at the electrode surface. Okay, another type of constant current coulometry, we call it secondary constant current coulometry, also known as coulometric titration. Okay, this is the special method for coulometry. So in this coulometric titration, one of the reactants, okay, titration is quantitatively produced, generated at an electrode from a precursor, which then stoichiometrically react with the analyte ion to be estimated. Okay, so this is another way of doing analysis using coulometry. Why we use this? We call it coulometric titration. What is good about this? The advantage of coulometric titration, so the preparation, standardization, and storage of standard solution are not necessary. So you don't have to prepare. For example, in conventional titration, you prepare, for example, acid base. Okay, you need to, this, for example, this is acid, this is base. Then you must add the indicator phenolphthalein. Okay, so you need to standardize the alkaline solution, the hydroxide solution. You have to prepare the solution, and also you must store the standard solution in to make sure that you will get the accurate concentration value for this titration. So in this case, coulometric titration method, okay, there is no need to standardize the titration. This is titration. Okay, so the quantity of the titration is related to the time and current. So this is T, this is I times T in the coulometric titration. Okay, so there is no need to prepare or to standardize the standard solution. Second advantage of using this method, in situ generation of titration or tetrametric reagent. Okay, so in this case, secondary constant current coulometric, or also known as coulometric titration, you generate titration at in situ. Okay, so the reagent will be generated in situ from precursor. Okay, so you will have this later on. I will discuss in detail about coulometry. So for example, this is the titration. Okay, so this is the analyte. Okay, so this is titration. So you will generate this, okay, the titration in situ at the working electrode. Okay, so why we need to prepare the reagent in situ? Okay, because there are no available standard solution or reagent to be used because of lack of stability, unstable reagent. For example, bromine, chlorine, iodine, ferric ion. So all these are not stable. So if you store these chemicals in bottles, okay, before you can use a month in one time, so you will see the compound or the chemicals are unstable. So it's not very effective in doing the titration. And also this coulometric titration is very sensitive. Okay, you can get to 4 significant digits, okay, in order to find the accurate value of the analyte concentration. Okay, look at this application of coulometric titration, which involve neutralization So what is neutralization? These two is called neutralization titration between acid and base. Okay, so this is to determine, this is the analyte. So this is to produce reagent. So this is the complete or total reaction. Okay, the secondary analytical reaction. Okay, so this, when you want to measure or to determine base, so you need to have reagent. This is acid. Okay, this is base OH. So this is acid H plus. So in order to do the secondary analytical reaction to determine acid, in the first case, you have to produce reagent. So in this case, reagent is the hydroxide. Okay, this is titran or reagent. So you must to produce this in situ hydroxide. So to react with the analyte. So this is analyte. So it will become neutral. Okay, water. So if you want to determine base hydroxide ion in your sample, so what is the reagent to react with the analyte? The reagent is H plus, the acid, okay, the proton. So how to generate in situ this proton? So you must have precursor. Okay, this is called precursor. So this water will oxidize. Okay, they release two electron to produce H plus. So H plus is the reagent. So then this is reagent. This is the analytes. So it will react. So you can check the endpoint by looking at the change of the color indicator. Okay, so then the neutralization, okay, is reached. Okay, so H acid react with base to produce neutral water. Okay, water. So this is called neutralization titration. So for precipitation reaction, so these two, for example, okay, so if you want to determine the amount of chloride, bromide, or iodide, or halides ion in your test solution, this is called analytes, okay, unknown. So you need to use reagent. So your reagent in this case is silver ion. So how do you produce this reagent? By oxidation of silver metal. So silver metal, this is silver metal, is the precursor. So it will oxidize, release electron, oxidize to form silver ion. So silver ion in this case is the reagent, will react with your analytes, yeah, either chloride, bromide, iodide, to form precipitate, silver compound, silver chloride, okay, silver bromide or silver iodide. Okay, depend on what type of halide ion present in the test solution. So this is called precipitation titration. Okay, and also this one, if you want to determine organic compound like mercaptans, so you also require reagent such as silver ion to react with the organic compound to form a precipitate. Okay, so if the next one is complex formation reaction, so these two, okay, to determine zinc, so you can use this is reagent. Okay, how does this reagent produce? How is this reagent produced? Is through reduction of ferrocyanate. This is ferric cyanate reduced to ferrocyanate. So the reagent will react with analytes. This is the reagent. We react with the analyte. Want to determine calcium 2 plus, copper 2 plus, zinc 2 plus, or lead, all these are divalent ion, cations. Okay, you can use EDTA. Okay, this is EDTA. So it will reduce to form this reagent. Okay, so the reagent will react with the divalent cation, for example calcium, to form complex formation of reaction here. So you can determine what is the amount of this one, calcium, the analyte, present in your test solution. For example, if you want to determine hot water solution, so you should determine the presence of calcium or magnesium in the test solution. Okay. Next, neutralization titration. This is example. Okay, so I talk about this neutralization to determine, for example, acid or base. So this is the precursor, a very simple precursor, which is water. Okay, so this water precursor, so it will here at the electrode. This is the electrode, the anode. Water as precursor will oxidize to oxygen gas, and this is the reagent. Okay, the proton ion at anode release 2 electrons. At cathode here, water as precursor will accept 2 electrons, produce gas, hydrogen gas, and this one. This is the reagent at cathode. Okay, so this is reagent at anode. Okay, for the reduction of water and oxidation of water. So at this side, the reagent, which is hydroxide, will go as titration. Will go out as titration, and you can put your sample here in the volumetric flask and put indicator. So in your test solution contain H plus. Okay, so when you look at the change of color, so you have determined the endpoint. Okay, this is the indicator, color indicator, or also you can use potentiometric method in order to check the endpoint. So here you can check the presence or the alkalinity of the solution by acid-base titration. So this is the reagent, acid. Okay, we'll go into this solution provided that you put indicator. Okay, either color indicator or using potentiometry indicator to determine the endpoint. Okay, so this is the reagent in the form of acid to determine analyte, hydroxide ion in your test solution. At this side, you also can use the reagent hydroxide to determine the acidity of your solution. Okay, so what are the precursor for both reagents, hydroxide and proton? The precursor is water. Okay, very simple precursor used to produce H plus and hydroxide as reagent. Okay, so this is called coulometric titration. So you will check how much reagent, for example here, reagent produced. So you will check the system, the integrator or the meter. So the I, okay, used in ampere. How long you do the titration in second time when you see the change of the color of indicator. So you monitor this, for example, if in this case is constant current 0.1 ampere for 5 minutes, which is 300 seconds. So you can calculate Q. Q equals to I times T. So 0.1 ampere times 300 second, you should get 30 coulomb. Okay. So this, once you know the coulomb, the amount of coulomb required to produce reagent, so you should find the mole of electron involved. Okay, this is coulomb per mole. Okay, so you will get moles. So then you can find the concentration of ion such as hydroxide or proton in your test solution by doing the proportional equation or calculation. Okay, next reaction involve redox reaction. Just now I talked about neutralization, precipitation, as well as complex formation reaction. Now is about redox reaction, coulometric titration involving redox. So in this case, you should produce reagent, for example, bromine. Okay, so how can you produce this reagent from this precursor, bromide? Okay, so bromine as reagent will react with either arsenic 3, okay, antimony, uranium, thallium, or so on. Okay, you can determine a lot of compound analytes, okay, present in your test solution, in your solution, in your soil solution, in your whatever solution to be determined, okay, the presence of each of these compound, okay, or substance. You can use bromine. Okay, reaction. This is you must produce bromine first. Okay, this is the bromide ion will produce bromine at anode. Okay, you need to have anode, then bromine will be as reagent. This is reagent or titrant will be titrated with the, for example, arsenic 3. So you can get the endpoint. So you must calculate how much bromine the reagent produce first. Then you relate with the analyte reaction between bromine and arsenic. So this one we will produce this and this back to bromide. Okay, so bromine will reduce to bromide. Arsenic will oxidize in this test solution. Okay, so this is reagent. Okay, so this is analyte. Okay, you want to determine the present, how much arsenic 3 present in your solution. So what you must do in this process is the redox reaction between arsenic 3 and bromine. Okay, so bromine will react. This is as oxidizing agent. So it will oxidize arsenic 3 to arsenic 5. Bromine will reduce to bromide. As well, similar to chlorine, iodine, and cerium 4. Okay, so cerium 4 as reagent. How can you produce reagent from cerium 3? So this is precursor, this is reagent. Then this reagent will react with which one in this. Okay, if you want to measure ferrum 2, titanium 3, uranium 4, arsenic 3, and ferrocyanide. So you can use cerium 4 plus or ferric ion as reagent. So how do you produce that reagent from cerium 3? Okay, example here is coulometric titration between cerium 4 and ferrum 2. Okay, so the reagent is cerium 4. Okay, will be generated in situ, electrochemically generated. Okay, by using this cerium 3 as precursor. Okay, this is precursor in order to determine ferrum 2 plus. Okay, so at anode, okay, and in the system, so serum 3 in the reservoir, okay, it's not reagent, this is precursor. So will oxidize to reagent, which is cerium 4 plus. Okay, so the cerium 4 plus generated will be used as oxidant titran in order for the electrically generated titran to be useful. Analytically, it should have a rapid reaction with the titran and the analytes. Okay, so this is just produced or generated. Then we'll react in the beaker or the coulometric flask. This is the analyte. So you will see the endpoint. So you stop the cell. So you can measure I with time until endpoint. Okay. So you will determine this one. Ferrum true. 2 with 100% current efficiency. Okay. So cerium 4 as reagent produced from this precursor at anode. Okay. So for example, this is cerium 3. So then it will go into the cell. So this is anode. This is anode positive. Okay. So it will generate cerium 4. Okay. So we'll go this as titran. Here in the solution contain ferrum 2 as analyte. So you will monitor the process of this titration between cerium 3 titran or reagent with this analyte. So when you see the endpoint, okay, you should stop the process. You will get Q. Okay, how long you do that, the titration? So this is constant. For example, 0.5 ampere times 610 minutes second. Okay, 600 seconds, which is 10 minutes. So you will get 300 column. Okay, so this is called coulometric titration. So next one is the control potential coulometry or potential static coulometry. V constant. Okay, so in this technique, the potential of working electrode is held constant. So what is held constant here is the potential, not current. The first one, we were talking about constant current. Here is constant potential. So the quantitative oxidation reaction of analytes can occur. The current is initially high, but decreases rapidly and approaches zero at the completion. Okay, so if you want to plot I versus time, okay, and also V, if you want to plot the graph V versus time, so V is constant. Okay, for example, oxidation 1 volt. Okay, so you just apply a constant volt for that electrolysis, then you can stop at the times required. So you can, if you want to plot I versus time in this process, so the time is, yeah, the current is will decrease with time. So this is Q. Okay, Q equals to IT. Okay, so the current initially high, yeah, high initially, but decreases rapidly, and approaches zero. Zero current. Okay, it means it complete. The reaction is complete. Okay, most of modern apparatus for potential static coulometry employs integrator to determine number of column required to complete an electrolysis. Okay, so but for I constant, if you want to plot I versus the previous method, okay, I times T. So the constant, I constant, so this is the area. So this is Q. Okay, this is for potential static. This is for galvanostatic. Okay, you can calculate Q, I. Okay, it's a constant times T. Okay, so you can calculate column. Okay, both sides. So if you want to plot for this reaction, V versus time, you should get the increase of current. It will flow this, okay, with time. Okay, so for potential static, efficient stirring is very important to for control potential electrolysis, be constant. Okay, so since all analyte species must be swept up to the electrode surface so that the electrochemical reaction is completed. So you must do, this is the magnetic bar, so you must stir the solution. So the efficient stirring is very important to make the electrochemical reaction completely occur on the electrode surface. So besides stirring, the ratio of the electrode surface to solution volume is also required. Okay, so this is the area versus volume. Okay, electrode surface to solution volume. So this ratio, electrode surface to solution volume, plays a role in determining the time needed for complete electrolysis, since the electric current will be directly, so the current I is directly proportional to the electrode area. So the electrode area surface, you must have very high surface of electrode, working electrode. So in order to make sure all substance or analyte can oxidize or reduce completely on the electrode. Okay, so the current, okay, the current Q equals to I times, so the current will be directly proportional to the area of the electrode as well as the concentration of the analyte. Okay, so you should relate Q equals to IT with the, so I is depending on A and C. Here, I times T. Okay, in the potential static coulometry. Okay, so you need to stir the solution effectively. Okay, so then the ratio of the electrode, you must have very high surface area of working electrode. So in order to confirm that the amount, the analytes can oxidize or reduce. Okay, so if your working is anode, so it will oxidize completely on the working electrode. Okay, if it is negative cathode, the analyte will reduce completely on the working electrode. So you must stir the solution, and also the electrode must very high surface area. So the application of potential static coulometry, there are a lot of application, okay, for this method. So for example, the analysis of inorganic compound, analysis of radioactive material, uranium, microanalysis, determination of organic compound, okay, synthesis of new organic compound, and you can determine the n values of reaction and how many electron number will involve in the reduction, for example. Okay, and also you can do multi-step control potential electrolysis. You can determine, for example, alloy ferrum plus copper, okay, for example zinc. So you can separately determine, okay, these two ion, ferrum 2, zinc 2, by using the potential static coulometry. Okay, there are a lot of application for this coulometry. Okay, the principle is measuring Q. Okay, so Q equals to IT as well as M and F. Okay, that's all for today. Thank you.